Now, what we just talked about in our homework today is essentially the trends on the periodic table, and I've got them highlighted here. Atoms in the bottom left-hand corner of the periodic table have low ionization energies. They are the least exothermic electron affinity atoms, and they're the largest atoms. But if you go to the upper right-hand corner of the periodic table, these have the highest ionization energies. It's hard to pull electrons off of them. They're the most exothermic electron affinities. So that means when they gain electrons, they become way more stable, and they're the smallest atoms. This is a gradual trend going from bottom left to upper right, but you can see that I've drawn a little diagonal line here across the periodic table in the p sublevel block. This essentially separates the atoms that we classify as large, low exothermic electron affinities and low ionization energies from the atoms up here, which are considered small. They are very exothermic in terms of gaining electrons, and they have high ionization energies. So generally speaking, the periodic table is broken up into two major classifications of elements. The ones on the bottom left, which have really low ionization energies. So that means they can lose their electrons easily, but they're not going to gain electrons because they have low exothermic electron affinities. So they're the ones that lose electrons easily. However, going to the upper right-hand corner of the periodic table, these elements have really high ionization energies, so you can't pull electrons off of them, but when they gain electrons, they release a lot of energy, so they gain electrons easily. So the elements, the chemical elements, the types of matter that fundamentally cannot be broken down into anything simpler, the atoms of those elements now can be classified as either easily losing electrons or easily gaining electrons. So we therefore break elements into two categories. They're called metals and nonmetals. And it's for the reason you see right here. The elements that lose electrons easily, we call metals. If the elements gain electrons easily, they're called nonmetals, okay? So let's focus in first on the elements that lose electrons easily, which are the metals. And I want to give you a series of properties that's true about all of the elements in this colored section on the periodic table. So we don't count hydrogen up here, that's not a metal. And we don't count all these guys above the diagonal line on the periodic table. Those are all considered nonmetals. The ones that are colored here are our metals. So what are the physical properties of metals? Well, they're on the left side of the periodic table. These are the elements with low number of valence electrons. So that's a characteristic of metals. Now, appearance-wise, metals have a luster to them. They kind of shine, right? So people and crows really like them. In terms of trying to hammer them, when you hammer them, they don't shatter. They bend into weird shapes. That's called malleability. So metals are malleable. You can actually make really thin wire out of metals. You can't do that out of something like sulfur or oxygen, but you can out of metals. So if you can create wires out of them, they're called ductile. Something else that metals will do is they conduct heat. And when we return to lab, you're going to learn that metals conduct heat if we're doing an experiment where we're heating up something with a Bunsen burner, like we're heating up a beaker on a metal ring stand. And it's the end of the period and you really want to leave. And so you're going to put the metal ring stand away after you've heated it for an hour. And when you touch that metal ring stand and burn yourself severely, you're going to remember, oh yeah, metals are good conductors of heat. Don't touch hot metal, right? They're also good conductors of electricity, which is a concept we'll talk about eventually this semester. And a really interesting thing about metals is when they react with water or dissolve in water, they form solutions that have a property known as basicity. They're basic, which is the opposite of acidic solutions, okay? Things like vinegar and like salsa, those are acidic, but water solutions of elements that are metals form basic solutions, okay? Now, what do they look like? Almost every single solid is considered brilliant white. And when things are brilliant white and they have a mirror type effect to them, they actually don't look white, they look silver. So people think metals in their elemental or their free state are silver. So you think of the metals you know, you've seen aluminum before, you've seen iron, you've seen silver. So those are all characteristic of what metals look like with a couple of exceptions. The element copper actually isn't a silvery colored metal. It's actually copper colored, but I didn't want to say that. So I said red. So copper is an exception. It's a red colored metal. Gold is actually gold colored, but I said it's yellow. So that's a couple of exceptions, but essentially every other metal on the entire periodic table would look exactly like aluminum or silver or chromium or lead, any other metal you may have seen before. It's that typical silver color. And they're all solids, except for one. Elemental mercury at room temperature is actually a liquid, which they use in thermometers, okay? Now, these are physical properties. It's what you can tell by looking at them or just measuring them. How do they undergo chemical reactions? Those are called chemical properties. And this is important. This is a key distinction between metals and nonmetals. Due to their low ionization energies of their valence electrons, they wind up losing their valence electrons when they react with atoms of other elements to produce positive ions. So metals react by losing their valence electrons. They produce, therefore, positive ions, and we call a positive ion a cation. Notice I said low ionization energies of their valence electrons. We had that question in the homework today where you saw the valence electron for sodium and potassium was really, really low, and then the core electrons' ionization energies were really, really high. You only pull off the electrons with low ionization energies. Those are only the valence electrons. So as we talk about what type of cations the metals form, it's going to be 100% based upon how many valence electrons they have, because those are the ones with low ionization energies that can be pulled off. Okay? So if we look at the periodic table, you remember before we've talked about how many valence electrons the elements have based upon their column on the periodic table. So if you're in the metal section of the periodic table, you're going to lose these valence electrons. So all the metals in the first column, they would lose their one valence electron. They always form positive one cations. If you're in column 2, you have 2 valence electrons. You're going to lose both those electrons. You're always going to form positive 2 cations. That's absolutely true. In the F and the D section of the periodic table, they're all going to form positive ions, but I cannot tell you what their charge is going to be because they form multiple amounts of different possible ions, because they will lose their valence electrons, and then they could lose some of their D or F electrons. I think Ms. Quigley asked this yesterday, somebody did, do the D electrons that are not in the valence shell have really, really high ionization energies? And the answer is no. So sometimes they can be pulled off as well. So if you have an element anywhere in here in the periodic table, you should know they're on the metal side of the diagonal line. They're only going to form positive ions, but I don't know what their actual charge is. Okay. Now, when you get over towards the right side of the metals, if you're in column 13, where there are 3 valence electrons, and this is boron up here, but that's not a metal. This is aluminum, gallium, and indium. Aluminum, gallium, and indium lose their 3 valence electrons when they react. They always form positive 3 cations. Here's what you're going to have to memorize, because when you're over in the D block, when you're in column 12, which is zinc and cadmium only form one possible ion. They lose their 2 valence electrons. They always form a positive 2 ion. And then in the 11th column, this is silver. Silver only forms a positive 1 ion. It's kind of a cute little pattern. The one in column 13, 3 of them make positive 3. In this column, 2 of them make positive 2. In column 11, 1 of them makes positive 1. 3, 2, 1. Okay? You'll need to memorize those because that's not necessarily intuitively obvious. These would be, they have 3 valence electrons. But these are in the D block. They could theoretically form more ion charges than just 1, but they don't. These 3 elements, zinc and cadmium, only make +2. Silver only makes +1. I would like you to know that. Okay?
Professor?
Yes.
So then for thallium, we just don't know how many.
But I'm going to tell you now, but that's correct, because it can form more than 1 cation. So thallium, which is way down here, right here, okay? Here's what it can do. Thallium can lose all 3 of its valence electrons and be positive 3. Or what these elements in the P block do if they're metals is sometimes the ionization energies only allow the P electrons to be removed. So think about thallium. Thallium is 6s2, 6p1. If the P electron is the only one with the low ionization energy, it would form a positive 1 ion, or it could lose its entire outer shell and form positive 3. So for thallium and the element below thallium, the possible ion charges are +3 or +1. Mr. Holmes, does that make sense?
Yes, thank you.
So now let's go to the next columns, and this should make sense as well if you got that. If you're in the 14th column, which means you have 4 valence electrons, The metals in this column could lose their entire outer shell, and they have 4 electrons in their outer shell. That's why they're in the 4th tall column. They have 2 s electrons, 2 p electrons. But sometimes these p sublevel metals only have low enough ionization energies to pull off their p electrons. So if they only lose their p electrons, they're going to form an ion charge of +2. So the metals in the 14th column either form +2 or +4 ions. If you're in the 15th column, you have 5 valence electrons. How are those arranged? 2 in the s, 3 in the p. You could lose all of your electrons and be +5, or maybe the ionization energies are only low enough to lose the 3 different p electrons, so you would be +3. So the metals in column 15 form +5 or +3 ions. And then finally, and this is where the metals end, there are a couple of metals in column 16. They have 6 valence electrons, 2 s electrons, 4 p electrons. You can lose them all to be +6, or if only the p electrons have low ionization energies, you'll only lose these 4 and be +4. Does that make sense? These are the ion charges I would like you to know for all of the different metals in the periodic table. Some of them you can say specifically they'll form 1 ion charge. A few you can say they're going to form 2 ion charges. And there's a whole bunch that you really don't know what their charge is, but at least I would like you to know that there's no way they form negative ions. They're only going to form positive ions. Okay? So this is important. And so I'm going to give you on your next homework just questions. I'll give you an element in the 1st column or the 13th column or the 16th column. I'll say, what are the ion charges going to be for the expected ions of this element to see if you know this pattern. Okay? Now, once again, focusing on the metals, what we do is we actually have some groups of metals that have characteristic names to them, and I want to point those out to you. All of the metals that exist in the 1st column on the periodic table, which we call group 1, they're called the alkali metals. They give them a characteristic name because they're all very similar to each other. We'll talk about some of their properties later. If you're in the 2nd column of the periodic table, these are called the alkaline earth metals. Spelled differently. If I ask you to write this on the test, I'm going to expect you spell them correctly, so make sure you pay careful attention to the differentiations between the names of the elements in the 1st column and the names of the metallic elements in the 2nd column. If you go all the way over to column 11, and you can see that's sort of near the end of the D block in the periodic table, column 11 has copper, silver, and gold in it. The elements in this column have a characteristic name. They're called the coinage metals because we make coins out of them, okay? So I want you to know they're the coinage metals. Then right before copper, silver, and gold, you have columns 8, 9, and 10. And there's 3 elements at the very top of columns 8, 9, and 10, iron, cobalt, and nickel. Those elements are similar in a particular property. They're called the ferromagnetic metals. Magnetic means they are magnets. And these are the 3 elements that are the most commonly known magnets of all the chemical elements. There's actually a few in the F sublevel that are pretty good magnetic elements as well, but these are the common ones. Iron is the most magnetic. Anytime you need to have a magnet, it's probably made of iron unless it's made of like europium or one of the F sublevel metals. Iron's a really good magnet. Here's what happens. If you have unpaired electrons anywhere in your electron configuration, then when the electron is spinning in one direction, it creates a magnetic field, which is something you're going to learn in physics. When one iron atom creates a magnetic field, it influences the atom next to it, and it creates an equal magnetic field that's parallel. And that influences the atom next to that, and that influences the atom next to that, until you get a giant chunk of iron where all the electrons and all the atoms are spinning in the same direction, and it creates a really big magnetic field. It creates a strong magnet. Other elements don't make such big fields as iron does, so they're not as good at magnets. But technically, nickel and cobalt actually are magnetic metals as well, although iron is the most magnetic of all. So that's an interesting property about these 3. The elements right below iron, cobalt, and nickel, and those would be ruthenium, rhodium, palladium, osmium, iridium, and platinum. These are called the noble metals. And you probably haven't heard of many of these except for maybe platinum. Platinum they make jewelry out of. Palladium they use to make white gold, actually. But all of these are very similar. They're called the noble metals for a very similar reason that we call the 18th column on the periodic table the noble gases. as we'll learn before the period's over, noble gases don't react with anything. So the word noble means they stay in their elemental or free state naturally. These metals do the same thing. They're not very reactive. So that means ruthenium, rhodium, palladium, osmium, iridium, and platinum can be found in their elemental state on Earth, and we can make jewelry and money out of them, just like copper, silver, and gold. That's why we make coins and jewelry out of them, because they're not very reactive. They stay in their elemental state, right? You wouldn't want to make like a piece of jewelry or make a quarter out of iron, because what does iron do? If you leave it in the backyard over the winter and it gets rained on, it turns to rust and it disintegrates away. So you don't want to make anything valuable out of a metal that will react away. You make things valuable out of metals that don't react away, that are inactive. And the most inactive metals of all are the noble metals and the coinage metals, okay? Now, we've talked about the D block for quite a while now in this particular unit. The D block are all metallic elements, and they actually go by a characteristic name called the transition metals. So if you ever want to talk about the D block, you can say the D block, but people will often call these the transition metals. The F block has a characteristic name as well. These are called the inner transition metals. And then this can be broken down into two rows, the top row and the bottom row. The top row, the first element is lanthanum. So the top row of the inner transition metals are sometimes called the lanthanides. Thus the name earlier yesterday, the lanthanide contraction, or 2 days ago. And then the bottom row of the F block, the first element is actinium. So those are sometimes referred to as the actinides. So I would like you to be familiar with these different nomenclatures for different groups of metallic elements, okay? Now, I'm going to show you some trends on the periodic table I want you to be familiar with. Metals vary in terms of their hardness. All metals are not really, really hard. Some are actually really, really soft. The group 1 metals in the first column on the periodic table, lithium, sodium, potassium, those are really soft metals. You can actually cut them with a knife. They're like cheese. But as you move from left to right across the periodic table, the metals get harder and harder and harder until you get to group 6, where these are the hardest metals of all. And then when you go past group 6, then the hardness starts to decrease and the metals get softer and softer and softer, okay? So if I color in a trend where green represents soft metals and orange represents hard metals, then if you're at the very left of the periodic table, the metals are like cheese. They become harder and harder. You get into the middle of the transition section, and those metals are really, really hard. And then as you move to the right, they get softer and softer. You've seen this before. You ever watch old movies about prospectors looking for gold, and when they find a piece of something they think is gold, what do they do to it to see if it's gold or not?
They bite it.
Because if it makes an impression with their tooth, it must be a soft metal, that would be gold. If it was like a compound like pyrite, it would crack their tooth and it wouldn't be gold. So that's how they would know that. And then we have mercury, it's a liquid over here too, so that's another reason. If you're making steel for buildings, and they're building all these extensions and widening the freeways, and they have all these steel girders in there, steel is made of iron. Iron's not too bad, it's in this column here. But what they can do is they can take iron and they can add a metal in the 6th column to it. And if they mix it together with the iron, it hardens the steel. Do you know what element they use to mix with iron in order to make hardened steel?
Copper? I mean,
Oh yeah, look where copper is. Oh, bad choice. Sorry about that.
carbon.
Carbon? Oh, carbon's way over here. Yeah, and it wouldn't be that. It's not. Yeah, that's not quite that. So, Mr. Holmes, or Mr. Orsinian, whoever it was that asked that, are you familiar with the song "Allentown" by Billy Joel?
No.
Oh, maybe your parents are. So sorry about that. So in this song, he's singing about this town in Pennsylvania. And one of the lines was, no, they never taught us what was real. Iron and coke, chromium, steel. What's in column 6 right here? What's the element right there?
Chromium.
Chromium. If you mix chromium with iron, you will get a harder form of steel. Chromium is one of the hard metallic elements. It's right in that perfect column, if that makes sense. Okay.
So wait, Professor.
Mr. Martinez, yes?
So from group 1, it's soft until it gets to group 6 where it's hard.
Yep. And then it gets soft. It's like a pyramid.
And then when it gets to group 16, it starts to get soft again.
Yeah, green means soft, orange means hard. So
Right.
you see how that works?
Green means, okay.
Makes sense? Yeah, you're correct. Now, next trend I want you to know is metal activity. How reactive are the metals, okay? And so in terms of metal reactivity, group 1 metals are extremely reactive. They would, actually group 1 metals are so reactive, if they touch water, they react with it. But as you move from left to right across the periodic table, the metals get less and less reactive. And the least reactive metals of all are in group 11, which we called earlier today the coinage metals. Okay, so group 1 metals are extremely active, and the activity decreases to group 11, with the noble metals, coinage metals, and Mercury being the least active metals of all on the periodic table. Now, here's what happens, kind of a strange trend. Once you go past column 11, all of a sudden the metals are active again. So the 2 metals up here, which are zinc and aluminum, are very reactive, and they get less and less reactive as they move down and to the right. Okay? So the trend in metal activity looks like this. So Mr. Martinez, watch the color coding. Orange means really, really reactive. So they get less and less reactive till they get to column 11, least reactive of all because it's green. Then past column 11, boom, these are really orange. Zinc and aluminum are really reactive. They get less and less reactive going down and to the right, and that's the trend for metal activity. So the second half of the trend is aluminum and zinc are very reactive, and their activity decreases down and to the right. So I would like you to use this pattern if you're going to predict between pairs of metals which one you think is more reactive and which one is least reactive. Okay? So those are the properties I would like you to know about metals. Physical properties, chemical properties, then we talked about hardness, and we talked about their activity trend on the periodic table. Okay? Let's go to the other group of the elements that exist, the ones that we haven't been talking about so far. So on the periodic table, they're these elements. These are the ones that tend to gain electrons easily because their ionization energies are so high, you can't pull electrons off of them. But their electron affinities are really exothermic, so they gain electrons really easily. These are called the nonmetals. And the nonmetals have a number of properties I would like you to know. First, their physical properties. They're on the very right side of the periodic table. In terms of valence electrons, these elements have high numbers of valence electrons. That's characteristic of nonmetallic elements. All the other properties are opposite of what we listed before. They are not malleable, they are not ductile, they don't have luster, they don't conduct heat, they don't conduct electricity. And if you dissolve a nonmetal in water, you wind up getting solutions that are acidic. So they would sort of be like vinegar or salsa or something that kind of like soury taste that kind of stings you. Okay, although you wouldn't want to eat that necessarily. Now, what do they look like? I cannot give you any overall unifying description of a nonmetal because they are very different from each other. The metals, shiny silvery, boom, that was it. The nonmetals aren't. Some are crystalline solids. One of them, bromine, is a liquid. Some are gases, so they vary widely into how they actually look. So we're going to talk about some of them individually. So I would like you to know what they specifically look like in their elemental state, but I can't say an overall description about all the nonmetals. But chemically I can, because they gain electrons easily when they undergo chemical reactions. They gain electrons from atoms of other elements, and they form negative ions. So the chemical properties of the nonmetals is that due to their high exothermic electron affinities, they can gain electrons easily, and they keep gaining them until their outer shell is full, and that produces negative ions that we call anions. I don't know, I'm sure Ms. Quigley would appreciate this. So I wrote this specifically. They keep gaining electrons until their outer shell is full. So let's say you have an oxygen atom that has 6 valence electrons. It would gain 2 till it has a noble gas configuration. Why doesn't it gain any more? Because now you have a noble gas configuration. And what's true about the electron affinity of a noble gas? It's 0, because the next electron would have to go into a new energy level. So once these nonmetals gain electrons, they always release a lot of energy to gain enough electrons to fill their outer shell. But once that P sublevel is filled in the outer shell, there's no more room for any more electrons. They're not going to gain any more because any additional electrons would have to go into a higher energy level, and that's not going to happen. Okay? Now, of these non-metallic elements that we have colored here on the periodic table, there's groups of them that have characteristic names. I would like you to know those names. Oh, let's go through the charges first. Sorry about that. So if we know how many valence electrons they have, we can predict what their ion charges are going to be because we know they will gain electrons until they reach a noble gas configuration. So if you're a nonmetal in column 17 where you have 7 valence electrons, you need to gain 1 electron to make a noble gas configuration. They're going to make -1 ions. These have 6 valence electrons. They're going to need to gain 2 electrons to have a noble gas configuration. They're going to be -2 ions, and the next column would be -3. Does that make sense? So if you're an element in any one of these 3 columns and you're on the non-metal side of the diagonal line, you won't form positive ions, you'll form negative ions, and you form enough to make a noble gas configuration. So you got to watch this diagonal line, because I give you an element down here, right where I'm circling, and I ask you what's the charge, and you say -3, that's 100% wrong. Down here, this is a metal. Metals don't gain electron, they lose electrons. This will either be +5, or it will only lose its p sublevel metal electrons and be +3. Okay. Questions on the charges of the nonmetals towards the right side of the periodic table?
What about boron, Professor?
So you tell me what you think it would be. Usually, so what happens is boron, it turns out, I don't want to say too much in advance, but there's going to be 2 ways in which elements can actually bond, ionically and covalently, which you may have heard before. Ions are formed when things bond ionically. It turns out boron hardly ever bonds ionically. It bonds covalently by sharing electrons. So there actually really are no ions of boron. But if there was, what charge did you think it would be theoretically?
-5.
Exactly. In the column right before that would be -4. But I just didn't put it there because ions really don't exist for those elements because they don't bond in this type of bonding called ionic bonding. So they actually don't really create ions. They share electrons. But if they did, theoretically, the trend would continue just as you predicted. Okay. Now on the periodic table, if you are in the 18th column of the periodic table, you are an element known as a noble gas. Okay, the word noble, once again, inferring that they undergo no chemical reactions. That's what that actually tells you. The column right before that, column 17, these elements are known as the halogens. And then finally, we have what's one way over here, hydrogen. It's really a unique element. It's not a metal, although in all reality, if you go to the Jupiter or Saturn, you go to the center of Jupiter and Saturn, which are essentially big balls of hydrogen gas. They just didn't have enough mass to cause the hydrogen at the center to fuse. So Jupiter and Saturn didn't become stars. They were too small. They just become gaseous planets. The hydrogen at the center of Jupiter and Saturn is under such high pressure, it exists as a solid, and it actually has metallic properties. But here on Earth, hydrogen doesn't have metallic properties, so we consider it a non-metal. And it's the only element on the periodic table that actually forms stable ions that are positive and negative. So that's really unique. It can lose its electron to be +1, or it can fill its 1s orbital with an electron and be -1. So it's a non-metal that's sort of unique. Okay. Now, nonmetal activity. Okay. Group 17 nonmetals are the most reactive nonmetals of all, and then the activity decreases moving towards the left and down. So the group 17 nonmetals are extremely active, and their activity decreases going down and to the left. So if I color in the most reactive metals in orange, this whole column is an orange column where this is the most intense orange color here. That's fluorine. That's the most reactive nonmetal. And the nonmetals decrease in their activity going this way. So if you think about metals and nonmetals, the most reactive metals are over here on the right, actually the bottom, or the left, and the bottom left. Their activity decreases going this way. So most reactive metal, decreasing activity this way towards the diagonal line. Most reactive nonmetal is fluorine, and the activity decreases going towards the diagonal line. So over here, they lose electrons really easily, and then they lose them less and less strongly. Fluorine gains electrons really easily, and then these other elements gain them less and less strongly, moving towards the diagonal line. Okay? Hydrogen, way over on the left side, it's not intuitively obvious from its position what its activity is, but it happens to be an active nonmetal. And then the noble gases, which are in column 18, I've colored them in green because they're very inactive. In fact, they're so inactive, they don't react with anything. And the word we use to describe something that doesn't react with anything is inert, okay? Now, if you notice what happened, both the metals and the nonmetals become less and less reactive as they approach the diagonal line. So the elements around that diagonal line are either really inactive nonmetals or really inactive metals, and that actually gives them a different property. The elements near that diagonal line are sometimes known as metalloids. And the elements that are generally classified as metalloids are the elements right above each of the steps on the diagonal line. That would be boron, silicon, arsenic, tellurium, and astatine. And then a few below, germanium, antimony, and polonium. These elements are really inactive nonmetals or really inactive metals, and they actually wind up having some properties of metals and nonmetals. They're elements with an intermediate number of valence electrons, but the key that we call them metalloids is because they do have some properties of metals and some properties of nonmetals. So on the periodic table, there really aren't like two distinctly different types of elements. I made it sound that way. There are metals and nonmetals. It's just if you're at the very left of the periodic table, you're really metallic. If you're at the right side of the periodic table, you're really non-metallic. And as you approach the middle or approach the diagonal line, you start losing your metallic and non-metallic properties, and you start developing a little bit of properties of the other. So when you get right to the diagonal line, we now have these elements that are questioning. They don't know what they are. They're either a little bit metallic, a little bit non-metallic, and so we call those metalloids, okay? Now, I want to talk about some individual properties of these non-metallic elements because I want you to know what they look like. Metals are easy, except for copper and gold. Every single metal looks exactly the same. It's a silvery, shiny, solid-looking material, okay? But the non-metals do have distinct looks to them. The first one I want you to know is hydrogen. Hydrogen is a colorless gas. And the interesting thing about elemental hydrogen is elemental hydrogen is not made up of millions and millions of atoms. The hydrogen ions have somehow bonded together to form what we call diatomic molecules. So I would like you to know that anytime you have an elemental form of hydrogen, which would look like a colorless gas, you're looking at billions and billions of hydrogen molecules, actually not hydrogen atoms, okay? Hydrogen, you may recall, is an active element. It's actually very light, so they used to use it in blimps. But because it's so reactive, that made it dangerous. And back in the 1930s, when the Hindenburg flew from Europe to New Jersey, it got too close to an electrical tower, and the hydrogen caught on fire, and the entire blimp burned, and 30 people were on the blimp, tried to jump out, and they would catch on fire, and they all died, and it was a big catastrophe. And so people decided, wow, hydrogen is just too reactive, too dangerous to use as a lighter than air ship gas. And so they actually switched to using helium, which is still lighter than air. It's just not as light as hydrogen, but helium is a noble gas and it doesn't react with anything. So we now use helium in our lighter than air ships, like the Goodyear blimp or the Fuji blimp, whatever. And helium, once again, if you looked at it, is a colorless gas. If you ever looked inside in one of those, you know, like balloons in Disneyland that you get, you don't see anything in there because the helium in there is colorless. But although it's not a diatomic molecule, that's important to understand. A gaseous elemental helium just exists as helium individual atoms. It's hydrogen, for some reason they pair up, and we'll learn why they do that next unit, okay?
I have a question, Professor.
Yeah.
Just like how for food coloring, that you put some food coloring into water and you can change the color, can we do that to gas at all?
Interesting question. You get food coloring is in a liquid form, so you mix liquid food coloring with liquid water, you can color the water. So if you have a colored gas, like let's say nitrogen dioxide, which is an orange colored gas, if you put that orange nitrogen dioxide in with either hydrogen or helium, then you would color the whole thing as well. Yeah, so that could happen. But it would have to be in the gaseous state. The coloring agent would have to be in the same state as what you're trying to color, either both gases or both liquids.
Professor.
Yeah.
So going back to hydrogen, say I have a sample of hydrogen. That sample is just hydrogen molecules, H and H.
That's what it is. Yeah. A whole millions and millions of H2 molecules for a reason that we don't know yet because this isn't unit 2. Okay.
All right. Thank you.
Professor.
Quickly, go ahead.
1 mole of hydrogen atoms is just H or
So
H2. I always mix that up.
So let me say it this way. Let's say you have 1 mole of hydrogen gas, okay? Because hydrogen gas molecules are diatomic. 1 mole of hydrogen gas would contain 2 moles of hydrogen atoms because each molecule has 2 atoms in it.
And that goes for all of them.
All the ones that happen to be diatomic like that.
Right.
1 mole of helium just contains 1 mole of helium atoms, but actually 1 mole of hydrogen gas contains 2 moles of hydrogen atoms because the molecules are diatomic.
Okay, thank you.
The next nonmetal, boron, is actually a crystalline brown solid that looks like this picture here. If you grind it up, it happens to look exactly like Nestle's Quick, and I know that because I had to use it in some of the research I was doing back in college. So that's a crystalline brown solid. Carbon is an interesting element. This is going to be a property I want you to understand that exists about several different elements. You can have crystalline carbon in the form of diamond, or graphite, or something called Buckminster Fullerene, or in the amorphous form called charcoal. Carbon can take on 4 different manifestations. It can look 4 different ways macroscopically. And that's because pure carbon, the atoms can actually bond together in different ways to form a crystal of carbon. So if you have this, which is a diamond, that's one form of pure carbon. If you have a pencil lead, it's made of this black material called graphite, okay? And if you have this powdery material, this is a type of carbon known as Buckminster Fullerene. So what's the difference between them? They're all 100% carbon, but the carbon atoms bond differently to make them. And sometimes an element can have its atoms bond together in different ways, and therefore you actually see it on the macroscopic level as looking like they're completely different substances, where they're actually made of the same thing. So these are called allotropes. They're forms of an element with different interatomic bonding. And so that means macroscopically, they have different properties. They look different from each other. If you are wearing a diamond ring or you have diamond earrings or have anything that's a diamond, the carbon atoms making up that diamond, each carbon is bonding covalently to 4 other carbon atoms. And that's what makes elemental carbon a diamond. If you look at any one of the atoms in the structure, look at this one right here, it's bonding to 1, 2, 3, 4 others. Every single one here is bonding to 4 others. When the carbon atoms bond to 4 other neighbors each, and that continues to the extent of the material, that type of carbon is called a diamond. Now, what's graphite? Graphite only has carbon atoms bonding to 3 nearest neighbors. And if it does that, watch what happens. It winds up making flat sheets. Look at this carbon right here. It's bonding to 1, 2, 3 nearest neighbors. When it does that, you get a really flat sheet. And so graphite is sheet, 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 all on top of each other. And you know what the sheets do? They slide over each other really easily. So if you make pencil lead out of graphite, you put the pencil on the paper and pull it, some of the sheets come off and it goes onto the paper, and that's why pencils can write. But in that sheet, the carbon atoms are bonded really strongly. So a sheet of graphite's really strong. It's just as strong as a diamond. That's why they make tennis rackets and things they want to be really light out of carbon fibers. Carbon fibers are made of graphite, and graphite's bonded like a diamond, but only in thin sheets. This bottom form, which is called Buckminster Fullerene, a kind of a strange name, they discovered only in the 1990s. And it's actually 50 or 60 carbon atoms that bond together in a spherical molecule. This is like a C60 molecule. And so that little brown, that black powder there on the right is just millions and millions of these little C60 molecules all stuck together, and it makes an alternate allotrope of carbon. Doesn't that look exactly like a soccer ball? It does. Well, it actually looks like something else too. It looks like that big old building at Epcot Center. Have you ever seen that before in Disney World? That is a geodesic dome. That was designed by the architect Buckminster Fuller. And because this form of carbon looked so much like structures by Buckminster Fuller, they named it after him, and they're called Buckminster Fullerenes is what they're called at this point. We actually discovered that in 1993, I think it was. And now we found that if you actually take measurements of infrared radiation and X-rays and stuff that come from stars and other galaxies, we can actually detect that there actually is Buckminster Fullerene that exists naturally in the universe, just we had never known about it until 27 or 28 years ago. So a new form of carbon. Charcoal is an amorphous form. What amorphous means is the atoms are arranged in a random fashion. So if they're arranged in a systematic fashion, that's called a crystal. So diamond and graphite and Buckminster Fullerene all have the atoms arranged in a repeating pattern. If the atoms are arranged in a random pattern, you have something like a charcoal briquette that you use in your grill in the backyard, and that would be an amorphous form. So that'd be a fourth allotrope of carbon. Okay. Now, the next element is nitrogen. This is what makes up most of our atmosphere. It's a colorless gas, and nitrogen, for some inexplicable reason as well, does not exist as millions and millions of individual atoms. They're diatomic molecules. So if Miss Quigley wanted to have a mole of nitrogen gas, she knows now she would have 2 moles of nitrogen atoms that make up that 1 mole of nitrogen gas. Oxygen looks like nitrogen. It's a colorless gas as well, but something you may not have really realized is that there's actually 2 different allotropes of pure oxygen. There's the O2, which makes up a good deal of our atmosphere that we breathe to be able to live. That's O2. There's another type of pure oxygen. It's 100% pure oxygen, but it's 3 oxygen atoms bonded together, and that's called ozone. Okay, so oxygen does have 2 allotropic forms. The ozone down here on the surface of the Earth is actually not so good for you. It's actually really irritating. If it gets into your eyes, it causes your eyes to burn. But it's really important in the upper atmosphere because what ozone molecules do is they absorb ultraviolet radiation. So when the sun shines down ultraviolet radiation on the Earth, if it made it all the way to the surface, we would all get struck by ultraviolet photons and we would all have skin cancer and we would die. But the ozone molecules absorb a lot of that, so it minimizes the amount of ultraviolet radiation that reaches the Earth. If you ever, really didn't lightning this last week when we had our rainstorm, but if you ever been outside after a lightning storm and you walk outside and go, oh, it smells so fresh and wonderful out here, you're smelling the slight sweet odor of ozone because during lightning strikes, oxygen's turned into ozone. So in a small amount, pleasant smell, gives you that fresh feeling when you're outside, but too much of it burns the eyes.
Professor.
Professor?
Yep.
Or I think someone said something before me.
Holmes, go first.
Yes. So if we had more lightning strikes, could we increase our ozone layer?
Yeah, it would go up from 0.0000001% to 0.0000002%. So it would increase it, but not significantly. Then Ms. Quigley.
I was gonna ask, there's like a certain process of lightning doing that. Doesn't that have a name?
You may be right, and I'm not a master on meteorology, but actually any type of high amount of electrical current will cause O2 molecules to be converted into O3. So the production of the ozone really doesn't depend upon what type of lightning happens. That's a high enough amount of energy to cause these molecules to be converted. And so whatever types of lightning there are, I really couldn't speak to that, I'm not sure. But it's just the high energy part of it is what actually causes the reaction to occur.
I don't think it's a certain name of lightning. There's just a term for air ionizers. It's the things that are in fans that produce ozone and stuff.
Mr. Julian,
I
thank you.
don't think that's what I was talking about, but
Just quickly, you're going to have to look into that because I'm really not sure.
okay,
So will you report back to us on that tomorrow?
sure.
Excellent, perfect. Okay, we'll be waiting. The next element I want you to know about is phosphorus. Phosphorus in its elemental state looks like this picture here. Now, when I look at that, I see purple, but unfortunately they call that red phosphorus. If you have samples of another allotrope of phosphorus, they call it white phosphorus, although it actually has a yellow color. And there's another type of phosphorus that's black. So there's 3 different allotropic forms of phosphorus. The white phosphorus is interesting in that white phosphorus is made up of millions and millions of P4 molecules. So there are a lot of elements, and they're actually in this particular column on the periodic table, the column that phosphorus is in, phosphorus and arsenic. They actually form an allotropic form in which the atoms create tetraatomic molecules. And so phosphorus does that. Sulfur, which is in the next column on the periodic table, that yellowish colored solid that you may have seen before, is actually made up of millions and millions of S8 molecules that are bonded together in a ring. So sulfur, when it's in its yellow form, is not sulfur atoms, it's sulfur molecules. And if you heat sulfur up, and this is going to happen in the lab on Thursday, you break the ring and you make a chain, and it doesn't look yellow anymore. So that's a different allotrope. So you can have different allotropes of sulfur if you break these rings and create chains out of them. This is one of the moons of Jupiter. Do you know what moon that is?
Titan?
Europa.
Oh, no, that's not Europa. Sorry. This one's covered with yellow and orange. It's covered with sulfur, not with ice. This is Io. Io has tons of sulfur in it. And the yellow color, excuse me, are the S8 rings. See the orange colors on there? Those are the rings being broken apart into chains. So you actually see all these different allotropes of sulfur right there on the surface of Io. Where does the sulfur come from? It comes from the interior of the moon. When they were first taking pictures of Io in the first Voyagers that went past there in the 1980s, they saw, oh my goodness, right here at the top, what's that? That was a volcanic eruption. Jupiter's gravity was tugging on the inside of Io so much that it caused eruptions of volcanoes to be occurring all the time. And the sulfur from the interior of the moon is deposited on the surface, and you continually have these eruptions going on. You can actually see that anytime you take a close picture of the moon Io, but that shows clearly all the different allotropic forms of sulfur. I just thought it was kind of a cool place in the solar system. Now, when you get to the halogens, you know how like if you go to the like into the ocean and there's fish that are really, really colorful, sometimes they tell you stay away from the really colorful fish. Those are the ones that are poisonous. Well, that's true for the halogens. The halogens are actually colored and they're sort of indicating to you they're not a good thing to be around. It's hard to see, but in that flask there is fluorine gas, and it's a very pale yellow-green color. I want you to know that's fluorine's color. Chlorine is also a yellow-green color, but chlorine has a more intense color to it, because you can see the yellow color a little bit more easily. So chlorine's a yellow-green gas. Bromine, the only non-metal that's a liquid, is an orange liquid, and it's really dark orange. It looks really dark there. And then iodine is a crystalline black solid, but it sublimes, which means turns into a gas, to make a violet vapor, which really means that iodine is probably not a black crystalline solid. It's probably really a deep purple crystalline solid. All of the halogens, when they're in their elemental state, exist as diatomic molecules. I would like you to know that, okay? So these are the appearances of all of the different non-metals I would like you to know, except for the noble gases. Let's do that now. We already did helium. Every other noble gas looks exactly like helium. They are colorless gases, and they do not form molecules. They're monatomic, okay? Now, last thing for us to know in preparation for the test for a week and a half from now, okay? On the periodic table, there are 118 elements, and there are maybe 20 something of them in which every single isotope is radioactive. And so I have colored on this periodic table all the elements that have only radioactive isotopes. And the key I want you to notice is every element whose atomic number is greater than 83, every isotope of those elements are radioactive. Because there's too many protons in the nucleus. You can't make a stable nucleus if you wind up having 84 protons or more. So element 83, which is bismuth, has a unique claim to fame, and that is bismuth is the element of highest atomic number that has at least one stable isotope. Once you go past 83 protons in the nucleus, no atom, no isotope will ever be stable. They'll all be radioactive. So this is the element of highest atomic number with at least one stable isotope. I've got element 94 colored in there. That's plutonium, and that's because if you search all over the earth for all the different elements and you try to find the element of highest atomic number that exists naturally, you'll find that we have a lot of uranium on Earth, whose atomic number is 92. But uranium, when it undergoes radioactive decay, actually turns momentarily into neptunium atoms, number 93, and then into plutonium atoms, 94, and then they decay down into smaller atoms after that. So the element that's found naturally on Earth with the highest atomic number, although it's in really small amounts, is plutonium. And there's not very much of it. So if you want more plutonium, you actually have to produce it. And in fact, that's what you have to do for every element above plutonium, elements 95 all the way up to elements 118. They don't exist naturally on Earth. We haven't found them by scanning the cosmos to see if emission spectrum data would tell us they exist. So all the elements above plutonium, and even including plutonium, are created in cyclotrons or in nuclear reactors where we smash atoms together and we try to do like what happens in the center of stars. We try to fuse nuclei together to make bigger atoms. So everything above plutonium is a synthetic atom. They've been created by scientists. They don't actually occur naturally. There's a couple of other little weird elements here. This one right here, atomic number 43, which is technetium, and atomic number 61, which is promethium, which every isotope of those two elements are radioactive. We've learned, if you study nuclear chemistry, that if you have odd number of protons or neutrons, that tends to make things less stable. Even numbers tend to be more stable. So these two smaller atoms, which happen to be, these two smaller elements, which happen to have only radioactive isotopes, are radioactive because their atomic numbers are respectively 43 and 61, and those are odd numbers and they just happen not to be stable. I got my periodic table shirt today, and if I could turn out all the lights and show you, my periodic table shirt has all the radioactive elements that glow in the dark, so that's actually really kind of cool.